I want to say something. For those who are suffering from post-Higgs depression, PhD, look at that. New opportunities in Higgs research. So get out of post-Higgs depression and get into post-Higgs dilemma. You're now trying to resolve the dilemma. So we are going to have a speaker, Ms. Carena, from Fermilab and University of Chicago, going to tell us about new physics opportunities in Higgs research.
Okay, so good afternoon. I don't know where I'm standing. Okay. So first of all, I would like to thank Harald for the nice invitation. I'm super pleased to be here. I have not had the opportunity to explore the beautiful venues of Singapore, but I'm planning to. So today I will talk a bit about new physics opportunities in Higgs searches. And so I will start with this funny slide that I borrowed from Alex. And so I feel that here, you know, we are in this slope. This is like going off-piste, where you want to try different alternatives that are a bit more exoteric. Today, I think I will decide to stay safe and in the slopes. And so I will try to think about, you know, how we can continue exploring with LHC a bit more about the Higgs that we have already measured, that we are only starting. I would say that I have to defend our field not very long ago, and someone told me, hey, the Higgs was discovered 5 years ago. It's old news, correct? And in reality, I think that the Higgs is only now that we are starting to understand precision measurements about that. So, if we're looking under the Higgs lamppost, there are many different possibilities. So the standard model valid up to the Planck scale. This is interesting, the fact that, you know, with the value of the top mass and the Higgs mass, we are really there at the edge of metastability. Then, of course, we have our all-beloved supersymmetry, and I will put some time on this today. We heard from Sven quite a bit yesterday. And so just in a nutshell, the fact that the Higgs mass has been measured to be 125 GeV tell us quite a bit about where we can be in the superpartner sector, especially the top quark. So this is the region that would be covered. And of course, this implies that the mixing in the stop sector has to be largish in the minimal sector, or that the stops can be heavy, should be heavy. However, this is a simplified scenario, and I would like to say that if one liberates more the sector of the stop soft masses, then in reality, one can accommodate one light stop with minimal impact on gluon fusion. So in reality, we need to search for it at colliders to say something about it. Of course, the other option is, you know, your minimal exercise is just put a singlet to supersymmetry. Again, then things change a lot. Then a Higgs of 125 GeV, this is what we are asking here, what it means a 125 GeV Higgs. Well, this is, as you see, then this is the stop mixing again. I can be all okay for no matter how small the stop mixing is, and I can be comfortable with low values of the stop masses. So in reality, so low tangent beta, when you put on just an extra singlet, is naturally compatible with tops at the electroweak scale, and that would say that we reduce the amount of fine-tuning. So in principle, the fact that supersymmetry has not been found at LHC yet doesn't really mean so much about where we are in our theories of supersymmetry. Of course, the other option is to think that the Higgs is not an elementary field, but it's rather a composite field. This is a beautiful idea that, of course, we have borrowed from the ideas of QCD. And so in this case, there is no Higgs. And again, you can have a 125 GeV Higgs. There is no Higgs about a certain scale at which there are some new strong interactions that turn on. And so this is very interesting because, for example, in these models in which the Higgs appear as pseudo-Nambu-Goldstone boson, we are not putting the Higgs ad hoc as we do in the standard model or in supersymmetry, but it appears just like a dynamical degree of freedom. There are other ideas that I will not talk about today that has to do with trying to explain the flavor in the standard model. This means the mass hierarchies and also the CKM by doing a flavor theory at the electroweak scale. And this is the models of Frog and Nielsen, that you put them from the Frog and Nielsen scale that is anywhere in the universe to the scale, to the electroweak scale, by using the two Higgs doublet models as flavons to create the masses of the fermions. What I want to say in all these ideas is all these BSM alternatives can affect the Higgs production and decay signal strengths at LHC. And so there's where we are today. We have the Higgs being 125 GeV. We have all the Higgs precision measurements that we have. And so we are trying to squeeze in the most information we can, trying to see if there is some, some guidance to where to go in these ideas of new physics. So let me just remind you very fast that in round one, Higgs properties were already in good agreement with the standard model prediction. But as you see, the bottom mass was on the light side, the top quark, that is not here, the top Yukawa coupling was on the large side. So I want to emphasize that a suppression, so this would be the bottom coupling suppression, is a very important measure, because a bottom suppression, a bottom Yukawa coupling suppression would affect all the branching ratios of the Higgs, actually in a more stronger way that it will affect the Higgs to BB bar branching ratio, and will demand suppression of gluon fusion rate and vector boson fusion from the measurements we have in order to explain a suppressed bottom Yukawa coupling. However, round two came. At the beginning, it looks like suppression of bottom coupling was still present, as we see here. But today, there is evidence of Higgs decaying to the bottom quark, both in ATLAS and CMS. And although there is still quite a bit of room to play with the bottom Yukawa coupling strength, things are not in highly strong disagreement with the standard model. Again, for the top, still there is an excess in the multi-lepton channel in the TT bar measurements, TT bar Higgs coupling measurements at ATLAS. So I just would like to remind you that the high luminosity LHC, the precision of most of these couplings will be better than or about a 10%. So if we can play with this in mind, then we know already that when we want to do something new in the Higgs sector, there should be a strong degree of alignment in the Higgs sector, which means that the Higgs that we see should be quite close to the standard model Higgs. And so based on that, I'm going to lead the rest of the talk, thinking about that only small departures from alignment are possible given the fact that we have these measurements of coupling strength and cross sections. Okay, so as I say, that on the standard model like Higgs, signal strength implies a degree of alignment. So what does it mean, a degree of alignment? So I will play with first with a two Higgs doublet model that is necessary in supersymmetry, but not only in supersymmetry. If you want to have a minimal extension, so a minimal extension of your Higgs sector would be a singlet, and next to minimal extension would be to have an additional Higgs doublet. In supersymmetry, you are obliged to have an additional Higgs doublet, and in particular, a Higgs doublet that couples in a given way to the top sector and the down sector. So the couplings of the Higgs, so if we have two Higgs doublets, then we have two CP even Higgses. And so the couplings of the two CP even Higgses to gauge bosons are given by these expressions. So as you see, when sin beta minus alpha goes to 1, then the light Higgs in this two Higgs doublet model has a standard model coupling to the gauge bosons. And in this two Higgs doublet model, I will consider a type 2 Higgs doublet model. And in that case, what happens is that one of the Higgses coupled to down quarks and charged leptons, and the other Higgs coupled to up quarks. And in that way, we are safe, besides when we go to radiative corrections, of flavor issues. So these are the vacuum expectation value. We have two Higgses. Tangent beta is the ratio of the two Higgs vacuum expectation values. In terms of the original neutral Higgses of the up and down sector, these are the two CP even Higgses. And if you look at the coupling of the Higgs to down fermions or the Higgs to up fermions, are given by these standard model values that are given in terms of the masses of the fermions over the vacuum expectation value of the Higgs, V. times these angles. Sine alpha is what diagonalizes the mass matrix in the CP even sector, and cosine beta, I just define it here. So what happens that if the mixing in the CP even sector is such that cosine beta minus alpha goes to 0, which implies cosine alpha is equal sine beta and minus sine alpha is equal cosine beta. So, sorry, cosine alpha is sine beta and sine alpha is minus cosine beta. What we see here is that the coupling of the lightest Higgs to fermions and to gauge bosons is a standard model-like. And so that would be precise alignment, correct? That the Higgs we have measured couples exactly standard model-like to the gauge bosons and to the fermions of the standard model. So this was proposed long ago by this gentleman. And I also want to emphasize that if I look here at the heavy Higgses, how the heavy Higgs couples to the down sector and the CP odd Higgs couples to the down sector, then these couplings are either tangent beta to the down sector, tangent beta enhanced, and to the up sector, if you look here, tangent beta suppressed. Okay, so what we are trying to understand now is what it means to have alignment, what it means to have these Higgs that we have measured being basically the standard, the Higgs that couples with the standard model couplings to the gauge bosons and to the fermions of the standard model. So in order to do that, I will just write the most generic 2 Higgs doublet model potential. This is beyond supersymmetry, so given in terms of the 7 quartic couplings and the masses. What we do, of course, I will not do that online here, but we can minimize do minimization conditions, and we can give the masses of the 4 Higgses, the CP odd, the char Higgs, and the mass matrix that will give the masses of the 2 neutral CP even eigenstates can be given after minimization conditions. And what we see here is that we can basically replace these parameters and these quartic couplings in terms of the CP odd mass, tangent beta, and that will define at 3 level the value of the neutral Higgses. When we got at loop level, now this is the loop level corrections, there would be a big dependence on the quartic couplings of the potential. In supersymmetry, these quartic couplings originally are given in terms of the gauge couplings, but in a generic 2 Higgs doublet model, these values are totally free, correct? So what we do here, we are going we have the mass matrix here, and we can decide to consider the eigenstate equation, which is what I rewrote here, and we see that the condition of cosine beta minus alpha equals 0, that is the condition of perfect alignment, can be given in 2 cases. One case is clearly when MA is large, so if MA is very large, this side of the equation would be naturally go to 0, and this is what we call decoupling. And the other condition is, of course, if we, independent of MA, if there is a relation between these contributions in the eigenstate equation. So if there is no additional CP violation for any 2 Higgs doublet model, we have that these conditions are the conditions of alignment in any 2 Higgs double potential. So if these are fulfilled, also the Higgs mass is given in terms of the standard model coupling times B squared. And so in this case, we will not expect any deviations from the couplings that we are measuring of the Higgs to gauge bosons and of the Higgs to fermions at LHC. Of course, as I told you before, we have not, we expect to measure these couplings at the order of 10% or a bit better for some cases by the end of the high luminosity LHC, correct? And because that's the case, it's of interest to study a bit what implies to have some small departures from alignment, okay? So now we are going to do that. And so, as I said, alignment might only be partially realized, so it's useful to understand what it means, this effect of small departures. In general, we parameterize things in terms of cosine beta minus alpha, that is our parametrization to quantize the level of departure of alignment. But one thing I would like to show here is that, as I told you, the coupling of the Higgs to BB bar is the one that, because it's the one that the branching ratio is largest, enters in the Higgs width, and therefore governs the couplings of the Higgs to all the other fermions and gauge bosons in a very relevant way. And I will use that in an important way. And the point is that if you do an expansion around cosine beta minus alpha, it happens that the real expansion parameter for the Higgs to BB bar coupling with respect to the standard model, that would be this value here, is this parameter eta, that in reality is given by tangent beta cosine beta minus alpha. Okay? And if we write this parameter eta in a 2 Higgs doublet model, in this case in supersymmetry, because I already replaced the values of the quartic couplings for what it should be, so we see that the value of eta is given by this expression. And from here, it already is easy to see that if the parameters, that these are the stop mixing parameter and the Higgs mass parameter in supersymmetry, if mu times it and mu are small, it's clear that all this part is going to be very small and would be basically this parameter eta would be independent of tangent beta itself, okay? So we see here that it will be very hard if mu is small to achieve alignment, because this is not going to be zero. This is the mass of the Higgs that is larger than mh, and this is the value of mh squared plus mc squared, correct? So it's already clear that alignment would be not easily realizable in the MSSM if mu is small, okay? Which means that if mu is large, we will have other issues that are coming to our rescue. So this thing that I'm telling you here, I'm going to show it exactly in this plot, and this is relevant for the searches that are done at LHC for the Higgs. So the point I want to make here is that if I look here now in the tangent beta MA plane, these are some searches for the heavy Higgses into taus that have been already excluded. And in these red lines, I'm showing to you the bottom coupling in the minimal supersymmetric standard model with respect to the standard model 1. So this means that this is a 10% deviation, this is a 5% deviation, okay, from the bottom Yukawa coupling. Okay? And as you see, it doesn't depend on tangent beta, because in this particular case, I'm considering a case with small mu. This is exactly what is done in the analysis here in CMS. And so by doing a global fit where we have measured to a given precision the Higgs to WW, the Higgs to CC, and so on, we say that this region of parameter space that would give a sufficient enhancement of the Higgs to bottom Yukawa coupling is excluded by what we say precision measurements of the Higgs. So what experimentalists are saying, we exclude values of the CPO mass up to 200, 300 GeV or 400 GeV just based on the precision measurements of the Higgs. Okay? So interpretations of Higgs precision measurements on these searches are actually important, but I will try to make the case that there is a strong dependence on in which situation we are, alignment or not, on how we reinterpret these precision measurements. So this plot would tell us that let's not look for Higgses below 300 or 400 GeV because they're already in the MSSM, correct? Let's just pause for a second. I am telling you this with the MSSM because it's something that most of you know and maybe love or hate. But this type of game I'm playing is actually possible to be done with any model of 2 Higgs doublet model that you want with some dependence on the parameter space. Okay, so this is just an example that I'm saying. So for moderate and large values of tangent beta and small mu, as we see, there's no dependence on tangent beta on this coupling. And so what we see is that all the vector boson branching ratios will be suppressed by the fact that I have an enhancement of the Higgs to BB bar. And so this is one case. So if in this parameter space, I look what is the value of the Higgs to WW with respect to the standard model, it will be suppressed because the Higgs to BB bar over the standard model is enhanced. So this is one case, and this is the case that I'm showing you now here. So now I'm doing the branching ratio or the coupling of the Higgs to WW with respect to the standard model. Before we have enhancements of Higgs to BB bar, which imply suppression of Higgs to WW. And based on that is that the experimentalists have put this bound on where we are not allowed to be, okay? But this is one case that as I try to explain, there is no we are quite far away from alignment. And so the only way to be compatible with the precision measurements is if the CPO Higgs mass or the other Higgses are heavy, okay? But however, there could be a more interesting case where mu is kind of larger, this Higgs mass parameter. And what I want to put you into your attention here, now the branching ratio of the Higgs to WW with respect to the standard model is actually equal to 1 here, which means that CP odd masses of the order of 200 GeV are allowed and perfectly in good health, okay, in this case with MSSM. So what this means, okay, is that if I am away from alignment, means that I have to have heavy Higgses because otherwise I'm in tension with precision measurements. If I am in a case where I can have very small values of MA, then I am pushed to have very large values of this Higgs mass parameter. So what this means is that, you know, we are always saying that the Higgs mass is putting us in tension with MSSM and so on, but this already, the fact that we have precision measurements of the Higgs couplings already tells us that we are in tension with naturalness, if you want, within the MSSM, because either we have large masses of the heavy Higgses or large mixing mass parameters, mass parameter for the Higgs. Okay, so this already is kind of disencouraging us of thinking about the MSSM. Of course, if we pause for a second, when we look at heavy searches, Higgs searches like the CP even and CP odd, this is very different because if we are close to alignment, the coupling of the Higgs to H set or to Higgs to HH or ZZ or the A to ZH are really suppressed because this cosine beta minus alpha goes to 0. And so the search strategies are very different. Close to alignment, the Higgs goes to BB bar and tau tau, okay? And these searches that are being done at colliders are actually very suppressed, okay? Instead, if we allow for some degree of alignment, well, the CP odd mass in this case should be certainly above 300 GeV or so, but we can look at these interesting cases where the heavy Higgs goes to 125 GeV Higgses, and these 125 GeV Higgses can decay to BB bar, tau tau, gamma gamma, and in fact there are many searches being done. So these type of searches are the ones done here, correct, where the Higgs goes to 2 Higgses, and you have all these searches where you search for BB bar, tau tau, and so on. So this would be this. Or you can be in a case where the CP odd Higgs goes to H set, for example, or you can also have the case into charginos and neutralinos. But let me just show this case, okay, because at least there is an interesting excess in Atlas, and I'm just reading for their paper. Mild excess of events observed at 440 GeV, mainly driven by the muon channel, local significance 3.6, Luxembourg effect 2.4. So maybe it's nothing to be jumping up and down, but there is an interesting excess in this Atlas result for a Higgs. This is for a Higgs going to set H, where then H is going to BB bar and set is going leptonic. To kind of summarize this part of the talk, so the complementarity between Higgs precision and A and H searches is very relevant. If we look in this tangent beta MA plane, what this tells us is that, for example, all what is shaded here is in these direct searches of the Higgses to tau tau, and these lines, above these lines here, down here, or this side of the lines here, are what is coming from precision measurements of the 125 GeV Higgs into gauge bosons, well, this is into gauge bosons actually. So what we see here is that for sizable mu, like these red lines, okay, what we see is that alignment, because we are in these red lines, correct? In reality, what is excluded at this moment is probably less than below 0.7, okay, so this area. So precision measurements don't put very strong constraints, as we saw in the CMS paper before. So when you are for sizable mu that is close to alignment, these precision measurement results are very weakened. However, the direct searches that are these red lines are very strong because for large mu you even don't have any possible decays of the heavy Higgses into other particles like charginos and neutralinos and so on. So your Higgs to tau tau is very strong. For a smaller mu, that are the blue lines instead, and this is mostly what the experimentalists have looked at, then of course alignment has very strong, implies that precision measurements already tell you that the Higgses has to be relatively heavy. Why this is important, for something that I'm going to tell you in a second, is because when we are below 350 GeV, this is what was known at the time I was young as the wedge, okay, is a region that is very hard to search for, okay? And so there are two regions that are very hard to search for. If you are above 350, most of the Higgses go into tops. And I'm going to show you now that it's extremely hard to search for the Higgs into TT bar, okay? Especially because you have very bad effects of interference with a standard model background. So it's very hard to look for the CPO Higgs above 350 because mainly goes to TT bar. And below 350, we have to work hard to understand, as I said in the MSSM, but you can do it in any other case, to understand this interplay between how much we can learn from precision measurements of the Higgs searches that we have and from direct searches of the heavy objects, okay? So probably I will go fast over this. So I would like just to show very fast that in the NMSSM, everybody knows, I think, that you have this additional coupling of the singlet with the two Higgs doublets. When this acquires a back expectation value, you kind of have a solution for the mu problem. So, and this gives you a mass of the Higgs that can be of the order 125 GeV without worrying about the stops. But what people don't realize so much is that when you are thinking now about alignment, this contribution is very important. And what is more interesting about this is that if you ask for alignment or close to alignment, which means you want to have some additional Higgses that are in the few hundred GeV and still be compatible with what are the Higgs measurements at LHC, then you are pushed in this coupling lambda to the lambda of alignment. And incredibly wise, this lambda of alignment is the one that is at the edge within perturbativity, okay, of the order of 0.62 to 0.75, so up to the GAT scale. And most important, gives you this precise alignment for low values of tangent beta, which is a bit of a miracle because there is no reason why this should be at this value. But having this value of lambda that you need to be there for alignment implies, from one thing, that you can maximize your contributions of the Higgs, and therefore you can liberate your dependent on the precise value of the stop mass in the NMSSM. So that's one thing. And the other thing is that if you also, you need also to ask, I mean, unless the singlets are very heavy, you also need to ask for some degree of alignment between the Higgs we have measured and the singlet. And when you do that, what you get is that this relation between the CP odd mass and the mu parameter. So unlike in the MSSM, alignment, so if this CP odd is alignment without the coupling, okay? So there are two options. If I put the coupling, then everything is very heavy and I wouldn't be talking. But if I want the Higgs mass to be within several hundred GeV, then this at the same time implies that the mu parameter should be reasonably small. So again, if I look at the NMSSM, there is a bit of a beautiful miracle that the fact that the Higgs is so close to the standard model values in their couplings to gauge bosons and fermions implies that in the NMSSM, the spectrum either is all very heavy and decoupled, or altogether brings values of the spectrum very at light areas, and you don't have any need of the stop. So you can have that also for light values of the stop. Okay, so the way to say it is that, again, alignment and naturalness come together in a beautiful way in the NMSSM just because of the precision measurements of the Higgs. Okay, so which I think is interesting. And of course, the Singlino also needs to be light, which is a very interesting situation for that matter that probably I won't have the time to observe. So the thing I would like to enhance here is that in this NMSSM type of situation, because of the alignment that you need to be compatible with his precision measurements, this heavy Higgs mainly decay into TT bar, and this is not easy. And then there are other interesting decays like the Higgs going to the standard model Higgs and the singlet-like Higgs, or the A going to the Z and the singlet-like Higgs. And I would like to stress that these searches are not being done, okay? Because the only searches that are being done is when you put the Higgs to BB bar to be within the mass of the Higgs, plus minus something. But if these Higgses are farther away, or these Higgses are farther away, you are really not performing the searches. They are a little bit, so this was there is a lot of need in order to look for example, these searches of the Higgs, as I said, where these two Higgses go to BB bar, because this light Higgs mainly goes to BB bar or to W, depending on the parameter, on the kinematics, but where these Higgs, could be anywhere between 50 GeV and 300 GeV or 400 GeV. Okay, so it's not close to 125. And then these searches should be redone by then liberating, instead of the C, transforming the C that goes to leptons into a Higgs that is 125. And in fact, we have used this analysis that is quite old, because it's with ATEV, to show that you can look in these models, okay, and the excluded are very little with this data, okay, and there are very big regions of, interesting regions of parameter space for light Higgses. We are talking about 200 here, 500 here, 300. This is a region very hard to explore, but there is a complementarity where you produce this singlet-like Higgs that goes to WW, oops, sorry, and then these searches, the blue points here are the blue points here, so this is excluded because you need to have the Higgs to BB bar over the standard model less than 10%, okay? And I think now there's analysis of Atlas that is a bit better, but they have not given the information in order to use this in this type of how much of this cross-section size branch ratio over the standard model is allowed in some Higgs that goes to WW or CC. So there are very promising searches that somehow, I don't know, Albert, why? Albert, why are you not doing this? Good. So this is the last plot from CMS, okay? It's ATV 19.8. 2015, we are 3 years later. Okay, so I want to use the remaining of my time, which I have no idea what it is, to tell you a bit the story of interference. The story of interference of Higgs physics with new physics. And there are three things I would like to talk about. So if in case I don't arrive to them, I tell you that right away. One is interesting interference that occur in searches of these Higgses to TT bar. This is a very important, because of course this is known since very long ago. This is 1991, correct? So you are searching for some bump or bump and dip over a big background, that is this TT bar background, okay? And you are searching for this signal. And I don't know if I will have the time to go into that, but let me just at least this slide walk you through. Okay, the signal we are looking for has the amplitude of the signal plus the amplitude of the background square. This is the amplitude of the signal square that we also call Bright-Wigner, the background square. And then, of course, there is an interference effect between these two. And this interference effect, of course, A square is the real part of A signal times A background star. In this case, the background is real, but could the signal not, so it doesn't matter where I put the star, of course. And so what is important is there are two pieces in this interference. One piece is the one that is related to so the signal is some loop function, some coefficients, and the propagator, correct? The propagator of S hat. And the background is a slow invariant function of S hat, so I just put C background. So there are two pieces here, that is the real part of the C signal times C background times the real part of this propagator, that is, I wrote it here, multiplying conveniently by S hat, okay? And then there is another piece that is the imaginary part of these coefficients times the imaginary part of the propagator that I wrote it here. So there are two different pieces, okay? What we call, let me call it real interference and imaginary interference. Of course, they are both real pieces, but one is coming from the real part of the propagator and the other coming from the imaginary part of the propagator. So this is the Breit-Wigner. As you see, this is asymmetric around around S hat. Okay, so this part here will give me some deep bump, or depending on the signal, some bump deep contribution. And all what it does really, when you integrate over the invariant mass of the differential cross section, all what this is going to do is giving me a shift on the value of the peak, a shift on the measurement of the Higgs mass. Okay? And so, sorry. In fact, this, no, I didn't want to do that. Okay, anyway. So this is the part we just discussed. Then this other part, that is the imaginary part of the interference, imaginary part of the propagator, well, this of course is going to be these coefficients, correct, times the sign of the difference of the signal minus the background phase. Okay, so when this phase, that's called usually the strong phase, is non-zero, so there is a new interference effect in this amplitude square that really cannot be thrown away. And in fact, this interference effect is going, because it's symmetric under around S minus m squared, is going to be in general a deep, could be a deep, or could be, depending on these values, or could be in the same direction of the Breit-Wigner, but in any case would be something that will add or subtract to the whole amplitude of the signal. Okay, and actually it's quite important in many cases. In particular, in this case, it's very important because we are having a huge background. Okay, so I will. I guess I'm just trying to see if the time will allow me. I hope so. So the challenge then is for this Higgs to TT bar channel is that, of course, if we are looking at this loop effect here, correct, the loop function as a function of square root of S over 2 times the mass of the fermion, of course, if this S hat is of the order of the Higgs mass, then for the top quark we are in this region, and there is no contribution for a light Higgs mass or to any imaginary part to this part of the loop function. But if this Higgs is above the top threshold, then of course, as you see, let's just concentrate in one case, that is the real versus imaginary. Here we have a plot for the CP even and CP odd. This is the dash and the solid. But look at the solid only, please. So this is real, okay? And this is the imaginary part. At the threshold, then we have the decreasing function of the real part and an increasing part of the imaginary, okay? And so, of course, at the end, the phase is given by the argument of the ratio of these two differences, and as you see here, this would be here the red line, okay? We have a relevant contribution to the imaginary part of this argument theta, of the imaginary part of this loop function. So the real interference from the real part of the propagator and the real part of the loop function is a shift in the mass peak that I will go back to that because this has been very much studied Higgs to gamma gamma. Okay, there are people like Lance Dixon and his gang have worked a lot on looking exactly to this shift, but not for this case, but for Higgs to gamma gamma, the standard model Higgs. Okay, because that gives you an uncertainty in how well you can measure the Higgs mass as a function of the width. So here. We have a piece that is going to give, as I said, the real interference, and we have a part that is the imaginary interference from the imaginary part of the propagator with the imaginary part of the loop function. And this changes the signal rate. And the problem is that, as you see here, okay, let's look at this case, correct? This is one case. Of course, depends on which is the mass of the CP odd. If the CP odd is somewhere here, correct, there is then there is some ratio between the imaginary and the real part. Okay, there's like pi over 4 here. When the Higgs that we are searching for becomes bigger, then the imaginary part becomes larger and the real part becomes smaller, and the effects of the imaginary part is important. And this is what we see here. Okay, this is just an example for all of them. But here you see the differential cross-section as a function of the invariant TT bar mass. So this is the Breit-Wigner piece. And then we see the Breit-Wigner plus interference. Let's just concentrate in the case of CP even Higgs. Forget that we have CP violation, okay? So the blue, as you see, in this case is a bump and a dip. In this case, when the CP even Higgs is 850 GeV, this search is a search that is a pure dip. And so there are very different searches at colliders if you are searching for a bump over the fast or the slowly decaying background of TT bar, or if you are looking for a dip and a bump, or if you are looking for a dip. Okay? And this search is only now, I will not go into this. I will not go into all these. So these searches are only now being considered by Atlas. And so the fact that we have this deep bump contribution in the resonant search of CP even or CP odd Higgs actually is a huge challenge for searches of Higgs to TT bar. Okay? And I won't go into these details, but I just want to transmit to you that only now has been the experimental collaborations have realized of that, and the results are very different once you start considering these contributions. So this is one interesting case. The other interesting case I want to mention is the Higgs going to gamma gamma. This is something interesting because I was working with my postdoc, Jean, on this AH to TT var because it's interesting for such a wide range of beyond the standard model searches for heavy scalars. And then we thought, okay, what happened in the real Higgs that goes to gamma gamma? Of course, now it's a different case because now you have to consider the right helicity, the Higgs to gamma gamma background. And so I will try to give you the nutshell here. So what we realize is that there is a novel probe of the Higgs total width that can be done by looking at the interference effect on glue-glue Higgs to gamma gamma, which has not been considered. And in reality, the point is that this interference effect has a different dependent on the width than the Breit-Wigner. Okay? Of course, the question is how big is the interference effect? Here looks small, and in reality is small. So this is now the big Breit-Wigner of the Higgs to gamma gamma resonant production. And then these are the interference effects. So the dashed line here is the real part, and all what this gives is a shift in the mass peak or in the mass measurement of the Higgs. And this here that I made bigger to make it visible gives a different contribution that also is relevant. And the interference from the strong phase actually changes the standard model rate by about -2%. Okay, and this is after doing quite a bit of calculation to look at calculations. And so, of course, if the precision we are looking at are of this size, then I think it's very important to try to make the point about understanding what are the effects. So let me just show first. I won't go into that because of time, but this is what has been done by Dixon and Lee some time ago. So this is considering the real part of interference. A lot of work has been done in going to next to leading order calculation of the background of glue to gamma gamma in order to understand this effect. We are not doing that. What we are doing is really looking at the strong phase in glue to Higgs. Okay? And in fact, as you see, this is not coming from the top loop for reasons already explained, but mainly is governed by the bottom loop. Of course, we were very excited with this. We also did the calculation of the part that the Higgs goes to gamma gamma that is very small, and the whole phase we got is kind of the 3% level, 0.03% level, which is pretty small. But then we realized that the background at 2 loop has actually a phase that is of the order of 0.2%. Okay, so it's really the calculation of the background, and this is where we asked John Campbell to join forces because we were VSM people doing this calculation, and we didn't have the strength to implement this 2%, minus 2%. No, it's 2% the delta, no? The delta background, correct? It's 0.2. I don't think so. No, it's the value of the phase here. No. Is the R, so is what, okay, let me just, because this is 0.4, you see, 0.4. The other one is 0.2, which is integrating over the whole region of this angular polar angle with respect to the beam direction. Here we get that the phase is of the order of minus 0.2, which is, I misspoke. So again, I won't go into that, but what is 2% is the effect of the, so it's here as a function of the width, okay? If you consider the cross-section, the interference cross-section, over the Bragg-Wigner cross-section is at 2%. So the interference is at 2%. The value of the sine delta, the delta is 0.205. So I misspoke there, I'm sorry. So the point, again, unfortunately, time is short. There are two things here. You see these scale uncertainties are huge, out of the order of the effect. So this really calls for an improvement of the QCD background beyond NLO, which I suppose is, my friend my friend John Campbell says, this is basically a 2-to-2, gluon to gamma-gamma. Matthias? No. Glue to gamma-gamma? No. I kind of believe John, so I'm sure not. So the point is that this high luminosity LHC will measure this effect. Then what is important here, correct, what I want to stress, is this is a unique piece that does not depend on the total width, okay, because when I do this interference term, so this is the cross-section, the Bragg-Wigner goes 1 over the width, but the interference effect is not dependent on the width, okay? So it has a different dependence on the width. And as a result, that means that you can go and measure, get information about the width on the Higgs production on shell, which is a total different measurement that you have on the Higgs width measurements that are off shell when you go in the tail of Higgs to ZZ. Correct? So it's a new, and this interesting point is that if you look at all the other measurements that you do in Higgs to WW, Higgs to CC, Higgs to 4 leptons, they don't have this interference effect. So they all go like this Bragg-Wigner, which means there is basically a flat direction, and they cannot resolve on the Higgs width on shell. Instead, this measurement is, of course, by the time that the high luminosity LHC will measure this Higgs ratio, Higgs to gamma-gamma over Higgs to 4 leptons with 4% accuracy, if that is the case, then we will go, this is 1.5 after some cuts on gamma-gamma. I don't have the time to explain, but this reduces the effect. So you will be somewhere here, 5.5, correct? And this means that you will be able to measure or to constrain the Higgs total width to about 14 times the standard model. You will tell me, well, now it's constrained to 4 times the standard model, but this is doing off-shell measurements of Higgs to ZC, correct? So this is really a novel improvement. Okay, so I don't have time to go into this. This is also interesting, but this is just, I will show you that also Higgs interference effect, in this case is if we add a singlet scalar interesting for the strength of electron phase transition and to explain baryogenesis eventually, then these interference effects are important. And for example, this is the analysis of searches for PP bar going to the double Higgs going to PP bar gamma gamma. With interference, this enhances the cross-section, is the black, and without is the dash red. And this area here is where you have a strong first-order phase transition. So this interference effect would be of interest if we want to also prove regions of parameter space for which we can try to exploit the possibility of sufficiently strong first-order phase transition. So I'm finishing here. I'm sorry, I'm done. So two things I want to stress. The 125 GeV Higgs, the Higgs precision measurements for a significant degree of alignment has important implications for the searches of additional Higgs bosons, as well as for dark matter, but I didn't have the time to look. But the fact, what I want to say, the fact that we have measured that the Higgs is sufficiently close to the standard model through precision measurements, tell us that we have to be, either everything is decoupling, and if it is not decoupling, then you need to have a relevant degree of alignment for the other Higgses of extended sectors to be light. And when that happens, this can help you a lot in fitting explanations for dark matter, for example, in supersymmetry. The last thing is that phase shift between a standard model and new physics can have important implications, provide novel on-shell information on the Higgs total width, and also like quark Higgs couplings. I don't have the time to explain that. It can enhance the LHC sensitivity to simple models with a strong first-order phase transition, and is for sure needed if we want to search for new Higgses decay above 350 GeV, where they decay into TT bar. And I will not read this because of time. Thank you.
Notice, I did not interfere with her in presenting the interference effect. Now, I think all the experimentalists should really realize we are in a quantum era, and you better look for interference effects, and not just say, well, this is the rate, that's the rate, but let us watch out for these little interference effects, okay? In view of time, there's one question or one comment. That's it. Any questions? Oh, yes. You already had your question. Sorry, yes.
Okay. Yes, Marcela, how much compatible or incompatible is the alignment condition in the MSSM with the possibility of having neutralinos as LSP?
Yeah, actually, there are blind spots. That means alignment means that you have the Higgses to be light, okay? And so you can have a well-tempered Bino Higgsino region that gives you the right relic density. And then you can have these blind spots where there is some cancellation for spin independent direct detection searches, where there is a cancellation between the part of the standard model Higgs in the S channel and the heavy Higgs that because of alignment you are putting it light, okay? And so you can have, it is compatible. There are regions of parameter space that are compatible both with a well-tempered Bino Higgsino region and with, actually there is a deep, I show this in a second, but without saying anything, this. So you have some region where you are, these are regions of parameter space that are very hard to look. So this is a blind spot. And this blind spot, I won't explain how it comes, but comes from the fact that you have a contribution from the standard model Higgs and a contribution from the heavy.
But usually you need the next to minimal supersymmetric standard model.
No, this is a standard model.
This is
in the NMSSM, you are even in a better situation because you can have two type of situations, the Bino Higgsino and a new well-tempered region that is Synglino Higgsino that is very interesting.
Okay, so
because of alignment, because this Bino has to be light.
So you're saying that the MSSM
it's not dead. It's the MSSM
is still alive.
It's still kicking, but you have to be sitting in these blind spots. You can't decide if you like that. Normally, you will be in this red thing, and this is excluded. Correct?
Okay, thank you.